Okay, so time to start. Lots of people here. Welcome. So we're having a test on Wednesday. Tomorrow is a holiday, and a week from today is also a holiday. So lots of holidays coming up. So does anybody have any questions about the test? So you'll get equation sheet, anything you need to know, periodic table as well attached to it. So if there's something that you feel that you need that's not on the equation sheet, you can always ask me. I'd have to give it to you, and there's also more space. So I know in this one it's kind of tight, but the one you'll get will have much more space so you can write in between. So anybody have any questions about the test, or should I just keep on going with the review then? All right, on with the review. So the rate of fusion of oxygen to some unknown gas is 0.935. What is the unknown gas? You get the Graham's law of fusion, where the rate of A over B is the square root of the molecular weight of them as such. So this is going to be 0.935 equals the square root of 32, x over 30, oxygen, we have oxygen to unknown gas. Oxygen, so it's x over 32, yeah, like so. Oxygen and some unknown gas, set that up. So you can square both sides. 0.932 squared is the unknown over 32. And 32 times 0.932 squared equals this. I think it's 28 if I recall. 32 times 0.932 squared. Where's the square in this one? It is in fact 28, and which implies it would be nitrogen. So oxygen is 32 grams per mole. Which one is 28 grams per mole? It's nitrogen. So recap for this one. What is the rate of effusion of unknown gas to oxygen? Or the oxygen to unknown gas is 0.935. What is the other gas? The Graham's law of fusion, set it up this way, solve for x, you get 28, which would imply nitrogen from that list. Questions with this one? Okay, this is another one you'll get the equations for. Actually, I should use the same color. Calculate the root mean squared velocity of nitrogen molecules at 25 degrees Celsius. You would get this equation, and it on the equation even says that m is molecular weights in kilograms. So you have to put in 3 times 8.314. 298 Kelvin for the temperature, all over 0.028 kilograms. So you put that in your handy dandy calculator. Three times 8.314 times 298 square root. Oh, wait a second. We're going to put the 9.028. Okay, 515. So this one is also just a plug and chug with an equation. The root mean squared velocity will be given to you. So just apply it. Put R, 8.34 for R. This is your temperature. And then molecular weight in kilograms. So 28 grams per mole, it's 0.028 kilograms per mole. Excellent question.
What is R?
The units?
Yeah,
The R is the gas law constant.
yeah.
That's also given to you in both values. So, why did I put it on there? Oh, geez, did I not put it on there? That can be changed. Oh no, it's there. Good. Yep. Other questions? Yeah. Okay. Use the following equation for combustion of octane. Calculate the heat of reaction for 100 grams of octane. So, 100 grams of octane. So it's dimensional analysis. 100 grams C8H18 times mole C3H, oh, that's C3. C8H18 all over 1.133 grams. Times 1118 kilojoules per 2 mole C8. So using this equation, for 100 grams of octane, so 100 grams of octane, convert mole of octane, and then the 2 mole octane comes from the fact there's a 2 right here to that amount of heat. And then just multiply it through. The last class wanted me to calculate everything out. Do you guys want everything calculated out, or do you just want the setup? Just setup? Okay. Good. Huh. Some I'll do the calculations. Like the next one, I'll do the calculation. So, but does this make sense for this setup? Questions with this? Okay.
114.33 is that already 2 C8H18, or is that just 1? Oh no, wait, there's 2 moles. Okay, never mind. Wrong answer. Okay.
Right there. And it's two moles octane per mole reaction, per reaction unit. So that's why you have to divide by 2 because there's the 2 to this ratio. Other questions? Okay. Oh, this one's horrible. Compound is found to be 30.45% nitrogen and 69.55% oxygen by mass. If 1.63 grams of this compound occupies that volume, that temperature, and that pressure, what is the molecular formula for the compound? Okay, so the idea, here is the idea. So get empirical formula. The empirical formula is the lowest ratio. And then get molar mass. To figure out formula. So this is how we do the problem. Gotta get the empirical formula first, which means the lowest ratio of nitrogen and oxygen, then get the molar mass to figure out how many formula units are in the thing. So we have 30.45 grams nitrogen, 69.55 grams oxygen. So percents, you can just turn it into a mass by multiplying by 100. Mole N per 14 grams nitrogen. Mole oxygen does 16 grams oxygen. And 30.45. This I do have to calculate out. This is 2.175. And this is 4.347. So we divide both sides by 2.175, and we get 1 nitrogen to 2 oxygen. So we have NO2 ratio. So where we're at right now, with the 30% nitrogen, 70% oxygen by moles, that puts us in a 2-to-1 ratio nitrogen to oxygen. And also NO2, this is 14 plus 16 times 2. So 16 times 2 is 32 plus 14, this is 46 grams per mole. So at 46 grams per mole, now we got to figure out the molecular weight of this. So the second part, we have 1.62 grams, that volume, that temperature, that pressure. So the way we figure this out, we got to figure out the number of moles. So PV equals nRT, which implies N equals PV over RT, which is so that's the pressure, convert to atmospheres, volume, 0.389 liters, 0.08206 liter atmosphere, mole Kelvin, 0, so this is 273.15 Kelvin. So just taking those numbers and applying to the ideal gas law, and in doing so, you get 7. This equals 0.17241 moles, and we have 1.63 grams. So 1.63 grams over 0.17241. So 1.63 divided by answer. And we get 96 for that. And actually, no, we get 92. Sorry. Well, I'll put we actually get. We get 94.5. And if you look at, compare that to so we have 94.5, and we look at 46 grams per mole. This implies 2 units of NO2. So we have N2O4 is our final answer. Okay. This one's horrible. Okay. Recap for this one. A compound is found to be 30% hydrogen, 60% oxygen by mass if 1.63 grams occupies 389 milliliters at 0 Celsius and 775 millimole mercury. What is the molecular formula for that compound? So first part is figuring out the empirical formula, and if we take the 100% and multiply it by, turn it into grams, we get a ratio of 1:2 for the nitrogen and the oxygen, or each unit being 46 grams per mole. Using the ideal gas law, we can figure out the number of moles to be 0.017, and then 1.63 divided that gives us 94.5, which is 2 units of the 46, which gives us N2O4. So, questions with this one? Okay. Can make, let me draw a picture for this one. Have a vessel, and then in this vessel, it's in water, all surrounded by water, and then in here, it's 25 degrees Celsius, and the total pressure, 745 milliliters of mercury, and 243. 43 milliliters. Okay, so we have some volume in there, and inside of this is actually water vapor and hydrogen. So we have a chemical reaction, and inside here we have hydrogen, and also with the hydrogen is water from the solution. So, what color should I use? I might as well just use red. So the pressure is actually going to be the pressure of the hydrogen plus the pressure of the water, or the pressure of the hydrogen is the pressure minus the pressure of the water, equals 745 minus, and it's 24 plus 721. So to get the pressure, we actually have to subtract the vapor pressure of water. It's given to us in the chart. So we have our total pressure of hydrogen actually being 721 millimeters of mercury. And same idea, solve for N. PV equals nRT. The question is asking for a mass of hydrogen. PV equals nRT, N equals PV over RT equals 721 ATM 760. Volume 243, 2243 liters, and 08206 liter atmosphere mole Kelvin. 298 Kelvin. like so. That gives us the N. I'll just go ahead and calculate it out because you have to multiply by 2. So 721 divided by 760 times 0.243 206 298. This equals 0.009427 moles, then 0.0094 times 2.016 grams nitrogen or hydrogen per mole hydrogen. This is going to be about 0.19, which is there. Okay. So recap for this one. We use magnesium hydrochloric acid to make magnesium chloride and hydrogen. Hydrogen is what we're interested in. We collect a bubble of hydrogen that has a volume of 243 milliliters, 25 degrees Celsius, and total pressure of 745 millimeters of mercury. We subtract the vapor pressure of water given the chart to get the pressure of hydrogen to be 721 millimeters of mercury. Use the ideal gas law, solve for the moles, multiply by the molecular weight to get the grams, as such. Questions on how to do this one? Did you have a question? Or some mumbling? Did I do the calculations?
Oh no, we saw 298 and we got it confused with 243.
Oh.
It's different because that's the volume.
Yeah, that's the temperature. That's Kelvin. That 298's Kelvin temperature, 25 degrees Celsius. Sorry, I just kind of throw it in there. 25 is used all so frequently. It's 298 Kelvin.
Yeah.
So, other questions? Okay. What amount of NO2? And we already know it's 46 grams per mole. We just solved that. In a 13-liter tank at 4.58 atmospheres and 3 to 5 Kelvin. So PV equals nRT. N equals PV over RT equals 4.58 13 08206 385, and then take N times 46 grams per mole to get the answer. Did you want me to go ahead and calculate it out, or is the setup okay? Raise your hand if you want me to do the calculation. People are straining in their eyes. Okay. What mass of NO2, which is 46 grams per mole, is contained in a 13-liter tank at 4.58 atmospheres and 3 to 5 Kelvin? So, ideal gas law, solve for N, get N, and then multiply it by 46 grams per mole to get the answer. So, sound good for that one? Questions? Calculate the temperature in kelvins of 2.2 moles of gas occupying 35 liters at 3.3 atmospheres. So
PV equals nRT, which implies temperature is PV over nR, which is equal to 3.3 upstairs, 3.5 liters, 3.2 moles, 3.08206 liter and sphere mole Kelvin, whatever that happens to be.
Okay, so ideal gas law, solve for temperature, plug in the numbers like so to get the temperature. Questions with this one? Radiation with a wavelength of 525 nanometers. What is the frequency?
So speed of light is wavelength times frequency, which implies frequency is speed of light over wavelength, 3 times 10 to the 8th, all over 525 times 10 to the minus 9 meters.
Plug that in your calculator. Raise your hand if you want me to plug it in the calculator, if that's good enough. Okay. I'll put, my cell phone's dying, but this one looks better than my actual TI calculator. And it's thinking, come on, cell phone. Oh, damn it. Sorry, I bumped. Okay, good. I bumped the power switch. So this is what you put in your calculator. So 3 times 10 to the 8th over 525 times 10 to the minus 9, like that. So, questions with how this works? Ooh, the dreaded Hess's law. I like Hess's law, but everyone else hates it. I'll give it purple. Delta H reaction. We don't know what that one is, but we're given these two. That's the delta H. I call this H1 and H2. So we need this, but we have these. So we have to decide where we're going to put these. And to start off with, make sure all the equations have the reactants on the left and the products on the right. So this equation here has S and oxygen on the right. S and oxygen are reactants, so we have to flip this one. The second one, SO3, is a reactant. I'm sorry, it's a product. This is in the product. That's the same side. Oxygen is a reactant. So this one we don't do anything. We leave it as is. So when we write these, so we need 2S plus 3O make 2 SO3. That's what we need, and we have
S plus O2, making SO2, and 2SO2 plus O2 makes 2SO3. So this is minus H1, H2.
So we need this 2S plus 3O2 makes 2SO3. And I've already flipped the other one. And notice that we need to have two sulfurs. So we're probably going to have to multiply the first equation by 2. So multiply this by 2, like that. The other thing you can look at is that there's two SO2s here. So you need to have two SO2s to cancel out those other SO2s. So that might also make you want to multiply the equation by 2. But now when you add them up, what happens is the SO2s cancel, and then these 2 plus 1 equals 3 O2s. So then we have 2S plus 3 O2s yields 2 SO3s, which is what we want. We have minus 2H1 plus H2. So then we go back to see what H1 and H2 is. So 2 minus 2 times 296.8 plus a minus 197.8. Whatever the heck this is their answer. Like so. Did you want me to put that in your calculator, or raise your hand if you want me to do that? Okay, sure. You guys like to know the answer. All right.
Yeah.
Minus 791.4. Okay. So recap. We are given these equations. We want to know this other one. So we need that one. So we flip the first equation to get the sulfurs on the oxygen on the reactant side, and we leave the second one as is because the SO3 is a product. Then we multiply the first equation by 2 to get the proper ratio of sulfur, or you can look at it because we need to get rid of the two SO2s. So either logic will lead you to the right answer. Multiply the top one by 2, you add them together, and you get the equation that you wanted, minus 2 times the first enthalpy plus the second enthalpy. So minus 2 times the first enthalpy plus the second enthalpy, we get minus 791. Questions with this one? Okay. Which of the gases in the graph below has the largest molar mass? The heavier gases have a narrow distribution. The lighter ones have a more broad distribution. So D is the heaviest and A is the lightest. So the answer is D. So questions with that one? That's kind of a more conceptual one. That one's just plain old D. Okay. So use the heat of formation to calculate the delta H reaction. So delta H reaction is equal to the sum of the end of products, H of the products minus sum of the N of the reactants, H reactants. That equation is given to you. Okay, so let's apply this. Delta H reaction is going to be the 2 times the HCl plus H2SO4 minus HS
SO2Cl2 plus 2H2O.
Like this. So I'm getting that because, so it's products, 2 HHCl, 2 from that, H2SO4, SO2Cl2, H2O. They're like that. And then I have to put in the numbers.
Okay. 2 minus 92 plus minus 814 minus 814 plus 2 minus 286.
Times minus 92 minus 814 minus the quantity negative 814 plus 2 times minus 286. 286. And 380. I don't get something wrong. What am I doing? Oh, what did I put some, oh, this is minus 364. So 364. All right. There we go. Minus 62. There we go. Okay, so this one, calculate the delta H reaction. The delta H reaction is the sum of the moles of products, enthalpies of products, minus sum of the moles of reactants, enthalpies of reactants. For this equation, it's going to be the heat of reaction will be 2 times the enthalpy of the product HCl plus 1 times the enthalpy of sulfuric acid H2SO4 minus the reactants SO2Cl2 plus 2 times out of water. Plug in the numbers from the chart, get the answer. Questions with this one? Okay. 2 ways to do this problem. There's an easy way and there's a hard way. I will do the easy way first. So drops from 4d to a 2p orbital. Rydberg constant is this. So we have 1, 2, 3, 4. So we have an electron in the 4 dropping down to the 2 and releases light. So the equation that you get is the delta E is the Rydberg constant times 1 over NF squared minus 1 over NI squared, and this equals minus Rydberg 1 over 2 squared minus 1 over 4 squared. So 1/4 minus 1/16 is 4/16 minus 1/16 is 3/16. So equals 3/16 times the Rydberg constant. Okay. So this is the easy way to do it. You do 3/16 times the 1 point, so it's 10 to the minus 2, 0.01097. That's the same thing as 1.097 times 10 to the minus 2. So 3 divided by 16 times 0.01097. And you get 0.002057. Now you have to invert this. 1 over 0.002057. So this is equal to 486.17 nanometers. So that's the easy way to do it. So, okay, easy way to do it. Now let's do it the hard way. So we have the hard way is delta E is 3/16 times the Rydberg constant. So, and this equals 3/16, and you're given the Rydberg constant to be 2.18 times 10 to the minus 18 joules. And, oh wait, I got that wrong. This is 4.09 times 10 to the minus 19 joules. And E equals H nu equals HC over lambda, which implies lambda is HC over E, which is 6.626 times 10 to the minus 34 times 3 times 10 to the 8th, all over 4.09 times 10 to the minus 19. So 6.626 minus 34 times 3 times 10 to the 8 divided by answer. And we get 4.863 times 10 to the minus 7 equals 486.3 nanometers. So 2 ways to do it. Get you the same answer. So, recap. For hydrogen, what is the wavelength the minute a photon drops from 4D to 2P in the hydrogen atom? Rydberg constant is that. Either way, you find out that the energy change is 3/16 Rydberg. This minus sign just means that the electron loses 3/16 Rydberg, so then the photon gains 3/16 times the Rydberg constant. And if you do it with the this one here, you do it that way, and you get a number. Then you invert it, which means you flip the fraction, and you get 46. If you want to do it the other way, you can calculate the energy of the photon using a different version of the Rydberg constant, and which is also given to you on the reaction sheet, on the given sheet. So you'll get 4 times 10 to the minus 19 joules, and solve for wavelength. Energy equals h nu equals hc over lambda. Lambda then is hc over energy. So h is Planck's constant, c speed of light over the energy, and we get 46 nanometers. So whichever way you prefer, the easy way or the hard way, I taught you the hard way before, whichever way you prefer. Questions with this one? Okay. So, how many photons are in a burst of yellow light from a sodium lamp that contains 609 kilojoules of energy? So the number of photons equals total energy all over the energy of the photon. So this is kind of like money. I told you this before. This is considered chemistry common sense. So instead of photons energy, let's think of money. If I had $20, how many 50-cent candy bars can I buy? So you would put your total money here and the cost per item. So if it's $20 for your money and 50 cents a piece, 20 divided by 0.5 would be 40. You could buy 40 chocolate bars. So instead of buying chocolate bars, though, we're going to figure out the number of photons, put the total energy and the energy per photon. Energy per photon, so the total energy is equal to 609 times 10 to the third joules. So don't forget the kilo. So the kilojoules, so where that comes from. And the E is h nu is equal to hc over lambda. So this is, we put this here, 6.626 times 10 to the minus 34 joules second. C speed of light, 3 times 10 to the 8 meters per second, all over 589 times 10 to the minus 9 meters. Throw that in your handy dandy calculator. 609,000 times 589 e minus 9 divided by 6.626 by 4 by 3 e8. Getting 1.8 times 10 to the 24 photons. So, yeah, answer C. Okay, so recap with this one. We're given the amount of energy and the wavelength of light. How many photons do we have? The number of photons is the energy over the energy per photon. So we're given that energy 609 times 10 to the third joules. The energy per photon is hc over lambda. Plug in hc over lambda, so throw it on your calculator, and you get 1.8 times 10 to the 24 photons, or about 2 moles of photons, if we're looking at it that way. So it's a lot of photons, actually. It's a pretty strong lamp. So 609 kilojoules, that's a lot of energy. So questions with that? Thing must have blown up. That's pretty strong. Okay. Calculate the wavelength of light associated with the n equals 1, n equals 3 transition in the hydrogen atom. So So we have, this would be an emission. So 1, 2, 3, and the delta E, we've just covered this as the Rydberg constant, 1 over NF minus 1 over NI squared. So equals minus the Rydberg 1 over 3 squared minus 1 over 1 squared. So 1/9 minus 9/9 is minus 8/9. So equals Rydberg constant times 8/9. I'd rather do it the easy way. So equals, what is the Rydberg constant? 0.01097 times 8/9. 0.01097 times 8 divided by 9. So this equals 0.009751. 1 divided by 0.009751 is 102 nanometers. Well, 102.55. Which is that. Okay. So calculate the wavelength of light associated with the n equals 1 equals 3 transition of the hydrogen atom. So going from 1 to 3, delta E is Rydberg constant minus Rydberg NF squared minus NI squared. So 1/9 minus 1 is negative 8/9. So plug it in, the energy change is positive 8/9 Rydberg. And then using the easy way that I just previously showed you is 0.009751 inverse nanometers. So you flip it to get the nanometers, and you get 102.5 nanometers. So, questions with this one? Nope. Okay. All right, there's a question like number 15 on the test, and I written, it's similar, giving the mass of the electron being 9.11 times 10 to the minus 28 grams. That's a little confusing. I've written 1.11 times 10 to the minus 31 kilograms right after that. So if you see that in my handwriting, I'm not trying to mess with you, I'm trying to give you a hint. Actually, you have to use the kilograms and not the grams. So the way this is given to you, the de Broglie wavelength is Planck's constant over the momentum. I wrote the momentum as mass times velocity. So 6.626 times 10 to the minus 34 joules times seconds. Mass 9.11 times 10 to the minus 31 kilograms times 3.66 times 10 to the 6 meters per second. And let's see here. 6.626 e minus 34 divided by 9.11 e minus 31 divided by 3.66. That's 10 to the 6. And I'm getting 1.99 times 10 to the minus 10 meters. Okay. It's that one there. Take a short chocolate break. My energy's dropping. It's a long day for me. I got lab and then I had to do this earlier today. Doing math takes a lot of energy. It really does. No, seriously. This consumes more energy than doing calculus. You take calculus. Calculus is more conceptual, but like doing math like this is like straight logic and brain power. It's the same energy demand as a jog, like as a light jog. It's about 100 watts, 100 watts of power. That's why, like, when you're done taking a test, you feel really tired. It's because you burn through a lot of energy. Which is also why I give you chocolate during test. Okay. I'm feeling better already. All right, so calculate the wavelength of an electron moving at that velocity. I take heed to my hint that you need to use the kilograms instead of the grams. And you'll be given the equation. The de Broglie wavelength is Planck's constant over the momentum, which is momentum is mass times velocity. So plug in Planck's constant, the mass, and the velocity, and you get 1.99 times 10 to the minus 10 meters. Questions with this one? Well, it's a tricky one. People hate this one. Determine the longest wavelength to remove an electron from a sample of potassium metal if the binding energy for an electron in potassium is 1.76 times 10 to the third kilojoules per mole. All right. So picture, here is our potassium metal, and then wavelength, the light comes in, electrons come out. And the binding energy is 1.76 times 1.76 times 10 to the third kilojoules per mole. So we need this. We need this in. We need this in per atom. So to get the photon, so what we do is we do 1.76 times 10 to the 6 joules. Where I'm getting the 6 from. 10 to the third kilojoules, and kilo is 1,000. 10 to the third is 1,000, so 1,000 times 1,000 is a million. So it's 1.76 times 10 to the 6. So we got the million. 1.76 times 10 to the 6 joules times joules per mole. Mole potassium to 6.02 times 10 to the 23rd atoms potassium. So 1.76 6 divided by 6.02 E23. And you get 2.92 times 10 to the minus 18 joules. So this is, that right here is the binding energy. This is per atom. So therefore, photon energy needs to be at least 2.92 times 10 to the minus 18 joules. So E equals H nu equals Hc over lambda
which implies lambda is hc over E, which is 6.626 times 10 to the minus 34 joules per second. C is 3 times 10 to the 8 meters per second. Energy is 2.92 times 10 to the minus 18 joules.
So you plug it in, 6.626 E minus 34 times 3 to the 8th divided by previous answer. And you get 6.8 times 10 to the minus 8 meters, which is 68 nanometers. And right there. Like that. So the trick here, the main trick here is to know that this fine energy of 1.76 times 10 to the third kilojoules, you need to divide that by Avogadro's number to get the binding energy per atom. So we're given that binding energy. So binding energy there, divide by the Avogadro's number, and that is then the binding energy per atom. Is this 2.92 times 10 to the minus 18 joules. Therefore, the photon needs to have at least that much energy. So then energy of the photon is Planck's constant times the frequency, which is equal to Planck's constant times speed of light over the wavelength, which implies the wavelength is Planck's constant times speed of light divided by the energy. Plug in those numbers, and we get 68 nanometers. Questions with this one? It's so easy. And we're going to hold the whole period. At a constant pressure, the combustion of 15 grams of ethane releases 777 kilojoules of heat. What is the delta H for the reaction given below? So, we want to know the delta H reaction there. So what is the reaction given below? So if you had me in lab, this is probably going to help you out. So it releases 777 kilojoules of heat all over 15 grams C2H6. Then, then mole C2H6. Oh wait, got it backwards. Let's go from the bottom. C2H6, that's 24 plus 6, that's 30 grams C2H6. And then we have 2 moles C2H6 for mole reaction. So 15 grams of ethane C2H6 releases 777 kilojoules. So we want to know the delta H for this reaction as written. Multiply this by 30 grams to get the moles. So now we're in this, the grams cancel, and this is then the energy per mole. But there are 2 moles of ethane for the reaction, so we multiply by 2 because of that there. And that's, so 30 divided by 15 is 2. So we're multiplying by 4. The answer is B. So not quite 800 multiplied by 4 is going to be minus 3120. I can put it in the calculator if it makes you feel better. So does this make sense? Okay.
Okay, combustion of titanium produces titanium dioxide. 2.06 grams titanium in a bomb calorimeter. The temperature increases from 25 to 91.6. The heat capacity is measured to be 9.84. What is the combustion per mole of titanium in this reaction? So, we have, and again, this helps if you just had me in lab. Q is heat capacity change in temperature. I know that you might see it as mass times specific heat capacity times change in temperature, but then instead you're given the heat capacity here, and it's right there. So our heat flow is 9.84 kilojoules per Kelvin times the change in temperature. I'm just write it as degrees Celsius is the same unit as Kelvin, but you can use them interchangeably, but not by multiplication division. You can not by magnitude. And this is 91.6 minus 25.
So we get our heat flow first. Heat flow 91.6 minus 25 times 9.84. I'm getting 655 kilojoules. Okay, so this is 655 kilojoules per 2.06 grams of titanium, and it's releasing heat, so it's the energy flow. The calorimeter is heating up, which means the reaction is exothermic. So it's exothermic negative direction, and then I don't know the atomic mass of titanium, 47.87. 47.87 grams titanium per mole titanium. Okay. Times 7.87 divided by 2.06. And this is 15229 kilojoules, which is minus 1.52 times 10 to the 4 kilojoules per mole. Like that. And I guess there's only a couple of you that have me in lab, but the rest are shooting the test Wednesday. Oh, and you don't have lab tomorrow because there's no class. Did you have? None of you obviously are in lab right now. Because we've been covering this in lab. That's why I'm like, oh, this should be easier. Okay. Okay, but so heat flow is heat capacity times change in temperature. You're given the heat capacity, so we figured out that our heat flow is 655 kilojoules. And for the heater reaction, that's the heat then that's going into the heat to the bomb calorimeter. So that means that the heat flow is leaving the chemical reaction. It's exothermic, so you have the negative. So negative 655 per 2 grams of titanium. So then multiply by 47 grams titanium per mole titanium, and we get minus 15,000 kilojoules per mole. So, which is that. Questions with how to do that? We got 5 minutes. Okay. I had someone ask me a question after class. I'll explain this in a little more detail. So in exist as 1, 2, 3. The quantum numbers, if you recall, n can be positive whole numbers only. L can exist as 0, 1, 2, onto n minus 1. And m sub l can exist as minus n plus 1, 0, n minus 1, n. Which means if L equals 0, m sub L has to be 0. If L is 1, m sub L can be minus 1, 0, or 1. If L is 2, m sub L can be minus 2, minus 1, 0, 1, 2. So the principal quantum number can be positive whole numbers only up into infinity. L is bound by n, can be up to n minus 1, it can be 0. M sub L is bound by, I'm sorry, I shouldn't do n, I should do L. I'm doing the wrong variable. Minus L plus 1. L like that. Had the wrong quantum number in there. So m sub L is bound by L such that it can be minus L integer steps up to L. So if L is 0, m sub L has to be 0. If L is 1, m sub L can be minus 1, 0, 1. If L is 2, minus 1, 0, 1, or 2. So let's look at it. One of these is erroneous. So if n is 1, L has to be 0. If L is 0, m sub L has to be 0. That's good. If n is 2, L can be 0 or 1. 1 is fine. If L is 1, m sub L can be minus 1, 0, or 1. Minus 1 is fine. If n equals 4, L can be 0, 1, 2, or 3. L being 2 is fine. If L is 2, m sub L can be minus 2, minus 1, 0, 1, or 2. 0 is fine. If n is 3, L can be 0, 1, or 2. L cannot be 3. This one's wrong. N is 3. L can be 0, 1, or 2. L being 0 is fine. If L is 0, m sub L has to be 0. That one's fine. So D is the one that's wrong. So specifically, it's L. Questions with this one? Okay. Determine the final temperature of a gold nugget that starts at 398 Kelvin and loses 8.45 kilojoules of heat to the snowbank when it's lost. So Q is M, specific heat capacity, change in temperature, or you can see Q over M CS is our delta T, which is 4850 joules, mass 376 grams, 0.128 joules per gram degree Celsius. So 4850 divided by 376 divided by 0.128. And this is 100 degrees Celsius. So if it's 398, so it's 398 minus 100. I guess it's 100.7. 0.7 is going to be 290. 7.3 Kelvin. So it's that one there. So this one here heat is mass times specific heat times change in temperature. We can solve for change in temperature. We get 100.7 degrees Celsius change in temperature. Initially 398 Kelvin, it's thrown in the snowbank. It's going to lose that temperature. So 398 minus 100 degrees is 298-ish, as shown there. So, all right, sorry to keep you after, but we're done. And let me stop the show. There we go.